I would like to talk about WebGL, but we're not going to do what you usually do with WebGL. We're going to do something slightly different. We're going to be creative with it. So today I'd like to talk to you about a few things, and I don't want to make you like scared or weirded out by the stuff that I'm going to talk about. So we're going to start off with what is WebGL and how does it work. And then we're going to have a look at shaders, because that's what we're going to do most of the time in this talk, which is a part of WebGL, but you can do much more around it. And then we're going to write some shaders. So there will be live coding, which can go either way. It might be fantastic. It might be terrible. We'll find out. So let's start with what is WebGL, because I only have 30 minutes, and I don't want to spend too much time on this boring lists. So first things first, we want to do as much work as possible on accelerated graphics hardware, which is usually the graphics processing unit, called the GPU in short. The GPU is a different kind of processor in most of our devices. Most mobile devices have one, most desktops and laptops have one as well, and they are very different in the way that they work. So one big difference that we can see is while our desktop CPUs, or even laptop or mobile CPUs, have maybe 4 or 8 cores, and cores being the physical thing, basically rocks that we tricked into thinking, right? So like they're the physical thing that actually does the calculations for us. And we have something like 4 cores or 8 cores, or if you have too much money, then you might have 16 cores. If you work at Google, you have like 32 cores. Fine, but it's a reasonable number. While in a graphics card, we can easily have 1,000 or 2,000 or 4,000. Now you're like, more is better, right? That's the classical, like more, just use more of it. So we want more cores, so we always do all our work on GPUs. Well, no, not quite, because the architectures have different like drawbacks and different characteristics. And let's have a look at what these characteristics mean. So CPUs have traditionally been done for regular programs as we run them pretty much every day. And these programs might do stuff like this. We have a loop, we read some data from somewhere in the memory, depending on our position in the loop. So we're starting somewhere in memory, and then we read consecutive values from memory. And then we check if there's a certain value in the memory. And if that is the case, we write some value to another place in memory. So what we're basically going to do is, imagine you have a long list, and somewhere in the list there is a 5. And then what this program would do is it would basically place a 5 for every other element in this list after the first 5 was found. Not very useful, but it's just like one kind of application where you see like we are reading from memory, we are writing from memory, and we have to like make predictions, and that's really tricky. And you can't really do this in parallel. Imagine if every one of you gets one box of memory, basically, where there's something in there. And now you have to define, or you have to figure out what you have to write into this box, or if you have to write something into this box at all, like put a piece of paper in at all, or if you just skip. You have to wait for what the person in front of you does to figure out, oh yeah, there was a 5, so I'm going to write a 5 down on my piece of paper, and then I'm like, I wrote a 5, and then the next person goes like, all right, okay, cool, yeah. So this is basically what's happening here. So we can't really do this in parallel. You can't just like start writing into these pieces of paper, so, right? So that's where these cores are pretty useless. We only have one core doing stuff here, and all the thousands others just sit there, do nothing. They're just idle, because we can't use them in parallel, right? There's a pipeline, and these CPUs have grown to be really, really efficient in doing things like predicting the future and doing stuff efficiently. Sometimes that goes wrong. That's called meltdown or spectra. If you heard about that, that's exactly what happens when you try to predict the future and you're not really good at it. Turns out this is complex, but there's other types of work where we can do things in parallel. So for instance, if you've ever had like advanced math in school, or have you ever had like computer science studies, you might have done matrix multiplication. Matrix multiplication works by basically I take this value and put it here, and I take this value, and so on and so forth, and I fill out these things. So I do not care about what is in the other cells, or I don't have to like branch somewhere or do some predictions. I just take a value, take another value, and write another value. That's all I do. I take one, take another, and put my result somewhere. So we can parallelize this. I can basically tell you which of these numbers you are responsible for, and then you can just do it, and we don't have to wait for anyone in the audience. So basically, you can all do it in parallel. You have to only like take 2 numbers, and then you get the resulting number, and you write that down, and then I collect the papers, and then we'll be good. So this is where the GPU really shines, because that means that all these cores can like take their numbers and do their thing, and then do it all in parallel, and done, we're done. Whereas the cores are like, I don't know. Do I have to, I don't know, do I have to, I think I have to wait for, no, do I, okay, cool, yeah. What was I supposed to be doing again? So, not really optimized for this. When we do graphics, however, we have exactly this kind of workload. So we do not want a CPU that is really great at these predictive things and these imperative programs to run our graphics operations. We want the GPU to do that because they're really good at this kind of work. So what can we do with this kind of stuff? Well, we can do things like this. We have a little ducky. This is in the browser, by the way, so you have a little ducky. You can touch that in the water, and then it has like these nice caustics and ripples. And that's fantastic and runs with hopefully 60 frames per second or faster. If you're in VR, it's probably faster. And we have a great time. But we're not going to do that today. We're going to do something different. And we're going to start by actually looking into how we get going with coding for this. So first things first, you need a canvas element. Who here has worked with the Canvas 2D API? Yeah, it's the same canvas. And then if you have done that, if you have used Canvas 2D, you know that you need a context as well. Well, the same goes for WebGL. Basically, you call it the same thing. You get a reference to the canvas element that you have somewhere on your page or that you have just created, and you get a WebGL canvas context. And then with this context, you just do the rest of the work, and then you're done. Well, OK, that's a pretty terrible explanation. It feels like this, right? You might have heard that before. Fun fact, apparently Twilio internally has this thing like draw the owl. So they have like an internal, unofficial mascot, I think. Like the owl is a thing. I've never seen it on any official merch. So like make that happen, please. God damn it. OK. Yeah, bam. So this is how it looks in more detail. And when I looked at that, I'm like, oh, OK, all right. Wow, all right. So there were like vertices. What? Buffers. I heard those about, like, there was something like that in Node.js, but I'm not sure if it's the same thing. I don't know. And then shaders, and then GLSL, and what the hell is going on here? I just want to draw pretty pixels on screen. So let's have a look at this step by step. So let's start, let's start with vertices. But first, have a breather. This is going to be fine. I'm going to introduce you just nicely into all these things, and we're going to have a great time, and it's going to be fun. So don't worry. I promise it's going to be all right, OK? So we'll have a good time. All right. So let's start with vertices. So if we want to draw any shape, in this case, I drew a really, really badly drew cube. We basically want to define the shape that we want to draw by plotting out some points in space. Now, points in space is exactly what is called a vertex, because mathematicians are very, very strict about wording. And they can be a pain in the lower back area when it comes to like being exact about wording. So they don't use points, they say vertex. Or in the case of the plural, it is vertices, because English is a complicated language. So here we have vertices, which are basically just points in space. Well, we can represent them somehow. We can also actually reduce one coordinate. For our means today, we're not going to do 3D, but basically it's just another number that we have to deal with. So we're just going to throw them away for the moment and just use two-dimensional coordinates. So here in this coordinate system, this would be where 0, 0 is. This is -1 on the x-axis and 1 on the y-axis. This is 1 on the x-axis and 1 on the y-axis, and so on and so forth, and then we get a shape. Cool. So if we want to do this in JavaScript, if we want to do this in the browser, we put this into a typed array, because that's the most efficient way, memory-wise speaking, to put this into memory somewhere. So this is still the regular main memory that your JavaScript main thread operates on. So now we have a typed array. We put all our vertices, so all these 4 values, which are tuples of 2, x and y, x and y, x and y, x and y. We put this into an array and make a typed array out of it. Typed array means we can't have holes. Matthias Binance has a fantastic talk on holes in this array. We can't have values that are undefined. We can't have values that are not a number. They are all float 32. Float 32 means it's a decimal number with a floating point part, so it's not a natural number. It's a floating point number, and it has 4 bytes for each of these numbers. 32 bits divided by 8, 4 bytes. So that means we have 4, 8, and so on and so forth bytes in this array. We don't really care about that, but we still have it in the main memory. And that's something that we do care about, because we want to access this really fast, and we want to make this accessible to the GPU. So we want to copy that over to our graphic card memory. So how do we do that? Well, it turns out the way you do that is called a buffer in OpenGL. And you just start like this. You create your GL is the context that we got earlier. So you use your context and you say, create me in a buffer, please. And that buffer is empty at the beginning. And now you're going to see something that is called really old API. OpenGL is over 20 years old, and it shows, because it's very, very stateful and very, very weird. So here we have this empty buffer. Can't we just pass in our vertices right away? No. The way we do it is we basically mark it as the current array buffer. That's just a constant. Basically, it's just saying, like, the next operation I do that touches an array buffer, please do this operation on this buffer that I just created. That is the empty buffer that we just created. Cool. Now, once we've done that, once we told WebGL, hey, use this buffer in the future, we can actually do something with it. And in this case, we say, there's some data that I want to put in this buffer that I just told you, and this buffer lives at array buffer, which is your internal pointer. And it's like, oh yeah, array buffer, I know what that is, cool. And then you put the actual data in. So these are the vertices from before, and then this is an optimization. We don't care about that at the moment. So basically all we do is we create an empty buffer, we say use this buffer, and then we put the data in. Okay, fair enough, not too bad. So we have a buffer, we have our vertices, all right, so we have points, and we now have them in GPU memory. Points in GPU memory is good, because that means that we can do stuff fast. Cool, so now that we're done with this nasty bit, let's look at the nicer graphics. And again, I poorly drew stuff for you. And I throw around money. Very Swiss of me. So here we have our GL buffer. And this is the first point. This is point A. It's x coordinate, it's y coordinate. B, x coordinate, y coordinate. C and D are down here somewhere. And the first thing that's going to happen when we start doing stuff with WebGL is this data is going to move into what is called a vertex shader. And basically, these vertex shaders, we're going to see what these boxes mean in a second. But basically, what they do is they get a coordinate pair, so x and y, and they run a function, and they change stuff, and then they return a new pair of values, basically, a new position. So that's what the vertex shader does, and there's lots of them. So basically, this doesn't happen like we don't start with A, and then we do B, and then we do... No, we do as many as we can based on the amount of cores that we've got in our graphics card. So this is actually pretty fantastic. If we have 4 points, even a potato has more than 4 shader cores. So here we go. We'll be fine. It's all going to be done in one step. Once these things are done, they give the input to another box that is called a fragment shader. What does this fragment shader do? Well, it takes a bunch of stuff, and it takes some output from the vertex shader, and then it transforms this. It runs code to transform this into colors on screen. That's it. OK, fair enough. We still don't know what these boxes mean, really, but let's get into that. So now we have our buffer. That's the thing that we just filled at the very beginning. And then we have a few shaders, and then we have pixels on screen. That looks less intimidating, I think. But let's get rid of these weird bits in the middle. So let's write some shaders. So what is a shader actually, really? Well, I kind of hinted at it already. It is a function. It's a function that runs on the GPU. So it means it runs a lot of times in parallel. Each shader core runs a function, a shader function, at the same time as all the other cores, and then they generate some output. So in this case, we might get inputs such as the x and y coordinate, and maybe some images, and maybe some light information, whatnot. Who knows what we're going to get? So basically, we can define these inputs mostly, and then they produce some output. In this case, the vertex shader, which is the first thing, it gets the x and y position and some other stuff that we define, and then returns a new one, a new x and y position that we're going to work with. Now, this shader is not really useful. It just returns the x and y that we just gave in, so it's not really helpful. What can we do with that? Well, if you think about it, so we have our shape, and maybe we want to have the same shape at multiple positions on our screen. So do we have to like change the buffer data all the time? Actually, no. If we just know the positions, we can actually just take positions somewhere else and use them to run the vertex shader. And basically what they can do is they can do things like scaling. We can just multiply our coordinates with something, and then we scale it up or down. Or we can use a matrix multiplication and rotate our shape. So we can do all sorts of these things without ever touching the buffer data, which is fantastic, because memory access is pretty expensive, but running these computations on the cores, because we have tons of them, it's like, yeah, whatever, just throw a core at it. right? Just, yeah, whatever, give it to core. Just don't bother with it. So basically, we can do that. So here we get a geometric change. So we can basically pretend that things are different than they actually are in memory. This is important because in 3D graphic, you want things, the same thing that is in front of you, if it moves away from you, it should get smaller, right? That's the way that we perceive the world. It's not necessarily reality, but that's what we perceive as reality. So you want to make sure that that happens without having to touch all the data in the buffers. So instead of touching the buffers, you basically just say, like, I have a distance, and I multiply or divide by this distance to make things that are further away in the distance appear smaller. So I just have another buffer with all the distances, and then I can draw the same thing from the same buffer at different distances with different sizes, for instance. This is called perspective transformation, and that's a typical use case for a vertex shader. We're not going to touch vertex shaders much today, unless I feel lucky and actually try to like figure out how the rotation matrix looks like, because I don't remember. There's books for it. I mean, come on. It's 2018. Just Google it. Anyway, I don't do whiteboard interviews, and if anyone ever like makes you do one, just walk out. Just go like, that's it, bye. Because I literally then asked the question, so do you have internet in the office? I said, why? Of course we do. Why are you asking me this question? We can just Google it. Anyway, moving on. I mean, or Bing it. You know, I'm not biased. DuckDuckGo is fantastic as well, I hear. So, which uses Bing, I think, but whatever. So now we have a fragment shader, which produces slightly different output. So now that we have the geometry settled and the first shader has run, we can use another shader to figure out for which position and kind of stuff of data, like we might have images here or whatnot. So basically, we have a position on the screen, and we need to figure out what kind of color we give this position. So we return a red, green, blue, and alpha. Alpha is just transparency. We set it to 1.0, which means no transparency at all, or to 0, which means entirely transparent. Entirely transparent is mostly bonkers because you want to see something on screen. So unless you work with transparency, ignore the last bit. Cool. So these are shaders. Well, no, but these are basically shaders. We're not going to write them in JavaScript though, because JavaScript turns out to be not very efficient when you try to like run that on the fly on a graphics card. We might get there at some point, but right now what we are doing is we use a language called GLSL, GL slang, or GL shader language, GL for graphics library. Cool. And how does that work? So, well, we have to get some data in. One way of getting data in is to set a constant. It's a bit boring to set a constant because it's not going to change, because it's in the name, it's constant. So let's look at more interesting things. Uniforms, for instance, are global variables that are available to both shaders. And we can easily set them from our JavaScript code, and then basically they change automatically in the shaders that are running. So that's pretty convenient. We can also use attributes. So if we have values that we need to set per vertex, so if we want to have the different corners have different colors, for instance, or if we have different distances or whatnot, I don't know. Basically, if you want to do anything that has a value per vertex, you can use an attribute. There's a limited number of attributes. I think it's 16 in WebGL that you can use, but basically that's your way to do it. So these are available in the vertex shader only because they are per vertex. Then we have the thing that is called varying, and that's an interesting one, because varying is being written in the fragment shader and being read in the being written in the vertex shader, being read in the fragment shader. So what we can do is we can basically say, like, yeah, we are at this vertex, we are at 0, and at this vertex, we are at 1, and then the graphics cores automatically will get values between 0 and 1 depending on which position they are at. And that's actually pretty funky, and we're going to see why this is very useful in a second. That's it for me talking. Oh yeah, I think I'm going to be fine in time. We'll have some time for shader programming. So here is an example page. Can you read the code? Nope. I heard a bunch of nope, so I'm going to make this larger. So I don't make it larger than this. Can you now see the code? OK, that's fantastic. Good. If not, then just come closer. I might zoom in for a moment. So actually, we ignore the vertex shader for the moment because it just passes data through. But what we can do here, so we see down here, this is the return value of our shader. And what our shader does here is it outputs the color. I can show you that it outputs the color by just taking something else in here. So vec is basically an array of values. And I want a vector of 4 values because we need red, green, blue, and alpha. So we start with 1 for alpha, and we go 1.0, 0, 0, 0, 0. What do you expect is going to happen? Wow, smart. Great. People are nice here. What happens if I say image coordinate, coord x? What do you think happens? Gradient, good. Good, fantastic people, you're amazing. And then I can do things like image coord y, which gives me this. But actually, it's nice because this language allows me some shortcuts. So it knows that the first two values come from this value, so we'll be fine, we'll be good. But then we can do interesting things. So for instance, I don't like the way that this coordinate system works because my 0, 0 is up here, and I might want to do something slightly different. So what I can do instead is I can say, all right, so how about we actually multiply the coordinates by 2? Because then we are like scaling things a little bit, and now the gradient is not as nice anymore, and we see like, okay, yeah, but the 0, 0 is still on the top left corner, it's still not very good. So how about we get something like vec2 position, and we take this, and then we use it here. And I say, okay, how about we move the 0 a little bit so that we get it somewhere else. Whoops, yeah. Typing, strongly typed, it's like, fine. So this looks weird now, and that's because the values to the top left of the middle of our wonderful canvas here are negative. But what happens if I make them absolute? Well, if I make them absolute, I get something like this. Still not very interesting, but at least we have like a 0 thing in the middle, and then we have like colors around it. So that's pretty fantastic. So what we can do now is we can basically get some math from the past, basically, and get some. Do you know how you get like the points on a circle? So let's figure out where on this radius of a circle we are here. So we can basically do this, and what we do is we get the square root of this value multiplied by itself. So we can do the dot product, which is just like p times p. So we do px, py, and multiply them with themselves. So we do this, and then instead of doing this here, what we do is we basically just use this as the, yeah, I now need a green value as well, it's fine. What? Float r squared, wait, what did it complain about? Something with dot, fantastic. I'm not having, right, yeah, it's a multiplication, I have to multiply it with itself. So there we go, but this is still not exactly what I want. I'd rather do something different, and what I'd rather do is I invert this. Oh yeah, it's 1.0. So if I invert this, then we have all the red within the circle. Great. Now what does this buy me? Well, not much yet, but how about we do something slightly different? What? Okay, was auch immer da hinten abgeht. Good times were had, apparently. So how about this? We have a vector 4, and we use 1.0 as our alpha value, so that we definitely see the colors. And we use texture 2D gives us the pixel value, so the red, green, and blue RGB from the image that we've got. So we have an image in the background. You saw that it's the RuhrJS logo, and we now give it the coordinates as well. So now we have that. That's not very fantastic. That's pretty boring, actually. But what happens if I multiply this with the radius? Then I already have, like, you see, I have this vignette effect, and I can maybe increase this a little bit as well, so I can type, get it a little brighter. And then I can do like weird things. So for instance, I have a uniform value. You remember this global variable that is set in the background for every frame to the current time. So I have a time in milliseconds here. And then what I can do as my last act, because I'm totally over time, interestingly enough, because I was super worried that I would not have enough content, but all right. There we go, apparently. What we can do here is instead of doing this, we do float px equals p.x plus sinus. So we take the sine so that we have something that oscillates between 1 and -1 sine of u times. So this is a value that keeps growing. So we basically get the sine wave. So we add something to this, and then we add something to the y coordinate as well. I'm going to be fine. It's going to be all right. I'm not running over time. No. Martin, you over time? Never. That never happened before. No, wait, this is actually px times px. This is what the dot product would have done. Plus py times py. And if I did this right, we get to this effect. And this is the stuff. This is the stuff you can do with shaders, and that's the start of it. I have a long list of shit that of things that you can build with this. So, well, you know, go play with shaders. They're not tricky. They're not magic, and they're not like weird. Well, they are weird, but they are fun, right? Just go and play. Just have fun. Enjoy yourself, and thank you very much. That's it.